Welcome Mechanics of Materials students. For this demo lecture, I'll be showing you how to deploy the handy-dandy equations that come from small twist angles and assumptions of torsional only deflection to a stepped diameter shaft. And this example comes straight out of the Vabel textbook in the chapter on torsional shafts, torsional circular shafts. But before we dive into it per se, we're going to just go over some of the great equations that we can derive for. I'll just point this out with my pen here. I'll go to another color. It's a little yellow here. So if we have a cylinder with the z-axis running up the center, and I'm writing in yellow now, try not to overwrite this too much, we can define an orthogonal set of axes and a coordinate system for that shaft. So we have z in the axial, r radial, and then we're define theta as a circumferential or tangential type direction. So instead of x, y, z, we have r theta z. Now, if we assume that all we're doing is twisting the shaft, and we're twisting it at a small angle, we can assume that all the deformation is going to occur basically shear and in the theta z direction. So we have no normal strains. We have, and we can basically assume that our r theta plane is undeformed. So that means no shear in the r theta, and also there's no shear in the z in the rz. Excuse me. So we have one type of shear, and that's or one type of strain. Excuse me. It's shear strain, not a normal strain, and it's in the theta z direction. So that's all we got. So Hooke's law gets really simple to apply. We don't have Poissons, we don't have the complicated elasticity equations. We just have basically shear stress divided by our shear modulus G is equal to our shear strain. If we walk through the deflections associated with twisting in that cylinder, we can relate the shear strain, that's engineering shear strain, gamma theta z in this case, is equal to the radius of the cylinder times the change in that angle as we advance down the axis of the shaft. So that's d theta dz. And the d theta dz term is sometimes known as the rate of twist. So how many radians of twist do we get for every axial distance down the shaft? So you can think of it a little bit like an index of a helix. You know, how far around you go for how far up, a bit like a pitch. So it's a pitch of the twisting strain. You can think of it a bit like that. So we can basically take this set of relationships and then take one more jump and relate the moment that would be required to get this shear stress. And we can get that by basically adding up the moment due to the shear stress that's being applied to an annular ring, and then add up all the annular rings. And as we do that, what we do in adding those annular rings together, we end up getting an RDA, meaning a bit of the cross-section area, the annular ring. And then when you add, if you combine that with our r from this expression, we end up with an r square dA of the cross section. And this term, if we add everything up together here, we notice, hey, r squared dA of a cross section is if I integrate it over my whole cross section, that's my polar moment of inertia. And if I happen to have a circular cross section, that would be represented by pi over 2 times r to the 4th, where r is the radius of my shaft, circular cross section. R is the radius of my circle. Okay, so we can take all of these relationships that we've derived just simply from the assumptions that we make for torsional deflection, keeping ourselves low twist angles, elastic range, eliminating all our other strains, applying Hooke's law, applying our relationship of applied moment to shear stress, and then hence to moment of inertia. Now we have our toolbox of expressions that are very easy to use that we can deploy to look at different applied torques or moments. That's our M sub z, different shaft lengths and diameters, and basically say how far have we twisted, and what is our actual shear stress as a function of applied torque, length of the shaft, radius of the shaft, and we can and our material properties. And then of course it's important to make sure we didn't yield, so we can then go back and relate what our calculated shear stress is in all of these cases, and say, could my shaft have yielded, or did I get close to my yield stress? So I'm going to step through the exercise from Vabel. We've got I call it a stepped shaft. And so we've got two sections on the ends that have a radius of 1 inch, and then a big thick center section with double the radius. And we're actually applying torque in 4 places at the ends. So we're basically applying positive moment, positive torque here at A at one end. We're applying moment in the opposite direction at B at this junction. We're applying positive again at C, and then negative at D. And of course all of these add up to 0 because the shaft it's in static equilibrium, we've assumed. So the first step I'm going to go through in deploying all of these great equations is I'm going to make a little map, like a shear and bending moment diagram, but this is like a torque diagram. So I'm going to in my mind, I'm going to kind of cut my shaft at any point along these lengths between applied torque or points. Now, I don't care what the diameter is yet, because I'm not looking at stress. I'm just looking at loading. So we're going back to statics here a little bit. So I'm going to say, well, what is basically the opposing internal torque for my positive applied torque at A? Well, I'm applying 2 times pi inch kips, so that's 2,000 times 3.14159 pounds times inches. And so if I'm applying it in the positive and I make a cut, that means the rest of that shaft is going to have to be twisting back, turning back in the negative. So all along here, I'm going to be opposing that applied M sub A. So I'm going to just say I've got 2 pi inch kip. When I get to this point, I'm going to basically start twisting back. I've got another applied torque of 8 pi. So if I were to cut the shaft here, the shaft on the right-hand side would have to be opposing whatever the sum of MA and MB is, which is -6 pi. So it would have to then apply +6 pi inch kip. Then I've got another application of torque here, 8.5, again in the positive. So again, if I were to cut the shaft somewhere here, the rest of this short bit of shaft over on the right hand side would have to be opposing M sub A plus M sub B plus M sub C, which are, two ones going in the opposite direction of the other two. And so I could basically say I'm going to have to oppose 2 pi inch kip minus 8 pi inch kip gives me -6 inch pi inch kip times pi, and now I'm going to add 8.5, and then that will basically say, okay, the rest of the shaft is going to have to go and give me -2.5 pi inch kip. Funky. The pi multiplier stayed there. You could multiply that and just get a number. And thankfully, what we find from that is that at our end point, our final applied torque at MD will basically be providing this, so we stay in static equilibrium. So what we've got in this diagram are basically values of M sub Z that are non-negotiable. We're not creating them by some kind of twisting angle that then we have to figure out the moment that we had to apply to get it. This is the applied moment. And so the internal moment in the shaft over those sections is fixed. So when we do our calculations, those are constants. So basically we can plop them into our equations, and then we can look and say, what stress would we need to have in order to achieve that? And what would be the resultant twist rate, or d theta dz, that would result from the combination of our shear modulus and our shear stress. And our shear strain, basically. We'll get that angle of twist through the strain. So at this point, we've got M. We have diameters, or radii, which is what we really need. From each of the radii, we can calculate an IZZ, and we're ready to basically say anything anybody would want to know about what's going on in the material in those shafts. So I am going to set this up on the whiteboard, and then I'm going to pause, and I'm going to show you an example of a very inexpensive, easy MathCAD program that I use to set this up, to basically design the shaft or look at the effect of different conditions, maybe bumping up diameter, increasing length on the fly. That's really useful for design. This will be even more useful if you had a little bit more complicated and interrelated problem like a beam, where you have several loading modes that matter. One nice thing about torsional shafts is we really only have one direction we worry about. And in this case, we're not going to be worried about fracture. So when we get our tau z theta, we'll be comparing that to material yields. Obviously, with a big, thick shaft, where we're very likely to be in plane strain, those of you who are going on to material science, this is the area that you would be probably thinking about applying your K1C, your fracture criteria, because you will definitely be in plane strain in the middle of something that big and thick. But it's for later. Just an aside, our plane stress, plane strain recognition, but for now we're just going to eventually be comparing yield criteria, so think more circles and yield. Okay, but first comes first. Let's look at our IZZs. So we'll have to have one for each different section, and as it turns out, we really only have two. We have in our basically our A to B and C to D, because we've got the 1 inch, and our IZZ is basically pi over 2 times 1 inch to the 4th, and then our IZZ in the middle, which is from point B to point C, is pi over 2 times 2 inches to the 4th, which is basically 8 pi inch to the 4th. So 1/2 times pi inch to the 4th, 8 times pi inch to the 4th. So quite a difference with that 4th power. And now we are ready to calculate twist rate. So we can basically use our IZZ here, some material property, a modulus, shear modulus, and our M sub z for each section, and so we can get a twist rate specific to each section. So we can start with a twist rate in our section A to B. It's going to equal our internal moment, M sub z. We'll just call it M sub z for section A to B. Divided by whatever our shear modulus is for the material, divided by IZZ in that A to B section. So our internal moment came from right there. And our twist rate for the next section is going to be the internal moment that we're going to encounter in that big thick section from B to C. Material hasn't changed, so our modulus is going to be the same. We will have a different polar moment of inertia because we got a thicker shaft, we got a different R. In fact, we got an R that's, 16 times bigger. So that's IZZBC. And of course, we've also happened to have, just because of the torques, the way we've assembled them, we've got a much larger internal moment, and it's going the other way. So the angle of twist is going to go the other way. Whoop, call that BC. And last but not least, we will have a twisting rate. We'll have the moment, the internal moment in section C to D. Material hasn't changed. It's very rare, by the way, to get a change of material. You would almost, for something like this, you could do, by the way, you could maybe do a butt weld and weld one material into the other. That gets dicey. In addition to the defects that you can have, there's a lot of issues with material mismatch. It is possible to have something like that. Generally speaking, when you're designing, you will always want to avoid abrupt changes in anything, whether it's dimensional changes. We saw the effect of that on stress concentrators. You certainly want to avoid sharp corners. Those are deleterious in addition to a section change, but you also want to avoid big modulus changes. Lucky for us, if you look at in your tables of materials, most materials that are really capable of being joined or that you would want to join typically have fairly similar moduli. So chances are your G is going to be at least within an order of magnitude for just about anything you pick and that you would conceivably want to join. If you're joining something with a collet or a collar or some other kind of complicated fastener, everything we're doing kind of goes out the window because you're going to have another material, you're going to have a different dimension, different considerations. So this very simplistic derivation would no longer apply. So, but the only thing that would apply would be a very fine butt weld where you've just abutted, literally, the two materials without any significant changes other than just that change in radius. So because of that, G is going to stay the same most of the time. And so of course for this last section we'll just complete this right up. We have our polar moment of inertia for section C to D. And of course that's going to come from here and there. And then this one's going to come in here. So if you want to know basically what the total twist would be, basically we can use our twisting rate and then multiply by the length. Because in all of these cases, the twisting rate doesn't change with length. So there's nothing in this expression that is a function of Z. Now, if we had a continuous taper, that would be a horse of a different color. We would have, if we had some kind of gradient like a fluid clutch or some kind of gradually applied torque, anytime we had that dependence on Z, then if we wanted to get our change in angle, twist angle, we would end up integrating, this dz according to whatever function we had. In this case, it's a constant, so it's really easy to integrate a constant. So basically all we have to do is multiply by the length. So we can basically, if we want our total change in angle from A to D, we basically do, the Z length from A to B times our twist angle from A to B and so forth. So just add them up and we'll add them by length as if we're integrating. We really kind of are integrating, except we're integrating a constant and something that's equal to 1, so it's a very easy integral, but you should get used to thinking that you basically are integrating that expression. And of course, each expression will be different depending on which section of the shaft you're on. So the big things that are changing in each of these sections are the polar moment of inertia, and because of the radius change, and we're also getting different internal moments because of the different applied torques, the positions of the torques. If we had just applied one torque here and one torque here, we would definitely have a different shear stress in each of the different sections, but we would basically have the same moment all the way through. We would still have different twist rates because of the different radii, and then again, of course, G is going to be the same. We're assuming it's the same material. So I'm just kind of talking through this and not doing a lot of calcs because I'm going to show you that on my SMath spreadsheet. Make it easy. So I can add up the total twist angle. This, in this case, is going to be positive, and this is negative, corresponding to the signs of my my internal moment in those sections that's having to oppose that applied torque. So last but not least, when I want to make sure I haven't yielded, I'm going to go back up to my expressions, and I'm going to combine that twist rate that I've calculated in each section, and I'm going to basically multiply out the shear modulus. I'm going to multiply it out, and I'm going to multiply by the radius again, following this formula, or any other variation that I've made up here, to get my tau z theta, my z theta shear stress. That's the one that I'm going to link back to yield material properties. So I can say tau z theta, we'll just say in this case within the section AB, is going to be equal to, I could multiply by the shear modulus if I already had, having already calculated my shear rate. I'm going to have RAB just multiplied. Not a quotient, it's a product. That's why I like writing, especially for torsional shafts. There are so many handy equations that we derive right at the beginning of our discussion of this topic. It's great to just basically make yourself a cheat card so you can go back and forth if you can't keep them straight in your head. They're so useful. So we'll basically multiply our shear modulus again, which will have the effect of canceling it out of the shear rate. But if we've already calculated a shear rate appropriate for that length of shaft, we put it in, and then multiply our radius across that section, and we use that to get our shear stress for that section. Then we would do the same for each section. Don't expect them to be the same, but if we are concerned about yield, we would then take the largest of our calculated shear stresses, and then we would compare that to our sigma yield for the material, remembering of course that sigma yield, if we're looking it up in a handbook, was probably done with a uniaxial tensile test, which would have a Mohr circle that looks like this. So if we look up in our handbook, we're getting this. So the corresponding shear stress in that test specimen that was used to define our yield strength is the radius of the Mohr circle, which is 1/2 sigma yield. So I'm going to take my largest tau and I'm going to compare it to 1/2 of whatever my sigma yield is that I look up for the material, and that is the same material that I use to get my shear modulus. So those two are going to go together. So I look up both for the same material. I use the shear modulus to calculate all of my properties for a given applied torque or a given applied required twist rate or total twist angle, whatever, and the part dimensions. And then having calculated my shear stress, I make sure it's within the material capabilities and include any safety factors. So that's it for the setup of the problem. If you look through the Vabel textbook, you'll see Dr. Vabel goes through several pages and calculates this, pretty much sets it up the same way, give or take. What we can do now that's great if we want to design or we want to look at the effect of changes, because we have such simple equations to work with, we can just load them into either a spreadsheet. You could do this in Excel, you could write this into MATLAB, Octave, any kind of simple high-level programming language. Another tool that I like to use for simple things is a MathCAD. It's sort of like a spreadsheet that you kind of write and type on, so it's a little bit more intuitive than a high-level program. So I'm going to take a pause and then come back and show you the MathCAD sheet that I developed for this particular problem, and walk through a few scenarios where we change different dimensions or apply torques, materials, and see what we can do about maybe making the shaft yield or looking at what the big levers are in terms of what we can and can't change, and the effect that it'll have on our deformation and internal stress. So stay tuned for that coming up next within this same lecture. Just going to pause. Okay, we are back. Hopefully you are seeing a new screen share view, the stepped diameter torsional shaft, and I'm going to walk you through my SMath sheet, which basically presents the exact same equations that we just derived or developed on my whiteboard tablet, and that you'll see in the Vabel text if you look up this particular example. So again, this is our circular torsional shaft with two sections, each of different length, that are 1 inch diameter, a middle section that's a different diameter. We're applying torque in 4 places, so we have 3 sections, each section of which has a uniform torque. We have a uniform radius over each of the 3 sections. So I like to start with the material. So just to walk you through what I've done here, I start with a descriptive name of what I'm doing, my step diameter torsional shaft. In this particular MathCAD, you can add text that is non-calculating, or you can add an equation definition which defines a variable, and in this particular one, which is SMath Solver, it's free. A lot of free documentation, a lot of a robust community. So I would encourage you to try it, mainly because it's free and also because it tends to be reliable. It has a units function, so you can define units for variables, and then those units will multiply along when you multiply 2 different defined variables together, which actually provides an automated units check. So if you say multiply, foot-pound, inch times inch to the -1, and you get something in just like kilograms, mass units, you define something inappropriately somewhere. I will not go through a tutorial for SMath, but just going to highlight some of the features that I think are useful, that you might find useful for your beam design project if you're doing that for this class or another class. So getting back to our step shaft, material properties. I am looking at my old book of material properties, and so I took a look at a ubiquitous stainless steel and pulled out a value for shear modulus, and I'm used to using the gigapascal numbers, and I just realized I actually added the tensile modulus, so I'm going to change that on the fly here. I'm finding a shear modulus for stainless of 11 times 10 to the 6 psi. So I have this in 10 to the 7th, so I would do 1.1 times 10 to the 7th. So now I have the appropriate shear modulus. For the same material, I've gone across and I've noticed it has a range of yield strengths, and that corresponds to the processing. So depending on whether it's annealed with big grains, or it's been cold work, or it's been heat treated, there's a huge range of yield strengths going from 30 to 160 ksi. I've decided that nobody's probably going to make a torque conversion shaft, which is something that has to have a certain minimum level of strength, out of something that's necessarily on the low side. If I were going to something with a higher fracture toughness, I might want to go to a grade of stainless that had a lower tensile strength, but because the shaft, depending on the bearings that it's riding in, it may require some wear resistance. So I picked 80 just as a middle number, and so that's 80 ksi. Notice we're 3 orders of magnitude different from the modulus, which is kind of what we would expect. So in the SI system, you get your strengths in like megapascals, moduli in gigapascals. So now we have basically 10 to the 6 pounds per square inch versus 10 to the 3rd pounds per square inch. I know that tensile yield strength was done uniaxial, so I know that it would correspond to a shear stress, so I'm going to call it a shear yield of half. So I just took this number, and you can see this is an actual SMath calculation. I multiplied 0.5 times the defined variable tensile yield. This is actually a defined variable that I defined up here. And I forced a unit conversion to keep myself in the pounds force and inch system. A note about SMath, and this is very likely true of all MathCAD, you cannot arrange the page such that a defined variable is defined and then utilized on the same basically vertical place on the page. So the page effectively reads itself from top to bottom. So if you define a variable and then you have right next to it an equation where you draw on it and bring it in and do a calculation based on it, you may see a little error that says undefined variable. Just move your second equation down the page a bit, and it will be happy because it will see it as defined. So there is a page placement function. Okay, so I've got materials. Basically, I have my big G, my shear modulus, and then I got something to compare my shear stress to. So now I can go through and I can use the results of my little statics problem where I define internal moment, and I can grab my critical dimensions. So I define different sections, because from the point of view of this problem, I really don't care about what's going on in the endpoints. I care about what's going on in the 3 different sections that are effectively defined by the changes in radius and the changes in applied torque. So had I had an applied torque right in the middle of one of those sections, I would have had 4 sections, and each one of them would have its own internal moment, its own radius, its own length. So it's okay, I can define as many as I need to, or I could define something that's a continuous function of z. In this case, it was stepwise. So in section 1, we have radius of 1 inch. It's, according to the problem, it's 24 inches long, and we defined the torque with our statics problem of a 2 pi kilo-inch pounds. So here we have, I just have the 1,000 multiplier inch pounds, and then here's my equation for my polar moment of inertia. So radius 1 is being raised to the 4th power, and that is the defined variable here. So I just go through and I do the same thing for each section. And I define a new variable for length, radius, torque, or in this case, internal moment. I call it torque here. I could have called it moment. That corresponds to the internal moment. I've defined internal moment as negative for the middle section, just for ease of use. Given my coordinate system definitions that we showed on the whiteboard, it really should be the other way, but I'll just be a little simpler here. So basically three sections, 3 lengths, 3 radii, 3 internal moment, 3 resultant calculated moments of inertia. So I can basically go on to my twist rate per section. So now, rather than going through more calculations, all I have to do are call in my defined variables. So I'd call in torque 1, I call in shear mod, which is gonna bring in the variable from up here, IZZ1, which I've defined up here, and lo and behold, I get a value in radians per inch. And I can do the same thing for the defined values for each section. And of course, in saying twist rate 1, I am now defining yet another variable, which I can then manipulate further, which we will do. I can add up, I can create twists from twist rates by multiplying by the lengths, and then I can add up all the twists to get a total twist. And of course, there is no unit on total twist because it's in radians. We basically notice when we multiplied the twist rate by the length, we ended up obliterating the units, canceled out, which is what we would have expected. And last but not least is are we going to yield? Here's our yield check. So now we use our expression for our shear stress appropriate for each section. So I have a tau 1, a tau 2, and a tau 3. And I'm using the expression shear modulus times radius times twist rate. I could have used a different combination, but this is the expression that I used on the whiteboard just earlier in the lecture. So I'm showing how this is so easy to calculate because all of these variables I've already defined further up in the sheet. So all I have to do is call them in by name and then adjust my output variables. So now I'm in a position I could do some design. If someone said, "Hey, I wanna make that middle section much longer. Let's make it 300 inches." So we can go ahead and change it 300 inches, and we can see that basically we had some change in our twist rate 2. Actually, not in our twist rate 2. We had a change in our twist 2 and in our total twist. Not a whole lot, but some. Bigger changes that we would expect, changes in our radius. So if we say our large midsection, we can look at what if we went to something like 5 inches. We can look at the effect of that. In this case, we had a huge reduction in twist rate. So basically what we did, this is looking at basically the change in our polar moment of inertia. We didn't change the internal moment, but we did change the area over which it applied, and we changed the moment of inertia. So we basically sunk that through the floorboard. So less deformation for the same applied force and the same applied stress. Importantly, we also changed our internal shear stress when we changed the radius. Not so much when we changed the length. So the length really only plays in going from twist rate to twist extent. So how many loops around the shaft is twisting. Okay. Big changes we might want to make might be things like the applied torque and radius combination. If we're going to come down here first off and do a check on stress, right now we could say that we have more than or maybe a little bit less than an order of magnitude safety factor. So we have 5 times 10 to the third as our largest shear stress compared to 4 times 10 to the fourth shear yield. So we could go up 10 times in our shear stress before we would have to worry about yield. Now, generally speaking, you're always going to want to have a safety factor of, say, 2. So we could basically say we never want to go above maybe 2 times 10 to the fourth. So we could look at what combinations of maybe a diameter decrease if we wanted to save weight. And if we're saving weight, maybe we'd want to go down to a 1-inch diameter on everything. There's a problem. We just tried to save some weight and I just yielded the shaft. Look at that. I just blew past my yield by quite a bit. So I believe I did. Let's look at order of magnitude. Maybe I didn't. 10 to the first, 10 to the second, 10 to the third, 10 to the fourth. So nope, but I certainly don't have the big safety factor that I did before. But now this one is one to watch. So I have 1.2 times 10 to the fourth. It's going in the other direction, but in terms of yield, it doesn't really matter. But basically, I'd be looking for this to go up to, if this got up to 20, I would be in trouble. But I could look at adjusting my torques. I could go, the first one I could go, look at what happens when I go up. We're not seeing as much of a change here. That's reacting, of course, in our first section. But basically, we can continue to make changes as we need. If we change modulus, we would expect to see a difference in our twist rate, but not so much our stress, because that's our modulus is going to affect deformation. Radius and our applied torques are going to be what drives our taus. So in any case, by plotting them out and giving yourself the ability to change variables one at a time, see how all the others react. This isn't a plot. It isn't showing a graph showing cutoffs. You're having to basically do your changes one at a time. But nonetheless, if you have your equations written out and you know the general direction things should change, if you're dialing something in or looking for, are you getting close to a threshold? SMath is a fairly nice step up from just doing something on paper by hand. It also has the benefit of you can throw in a little graphic. You have all of your equations right there. You can use units. The auto units check is kind of nice. This is the type of thing, like I said, that is useful for a first pass design. Where you would step up from this would be basically using either Excel or using a program where you would calculate thresholds with given constraints. What is the smallest shaft you could have? What is the largest torque you could apply? So, solving for those extreme as opposed to kind of having to do it hunt and peck, iteratively calculating. But at the very least, you do not run the risk of fat fingering something on a repeat calculation. So that is it for our stepped shaft. And for those of you who are taking this in spring 2022, this lecture would accompany the circular torsional shafts and would be useful maybe as a prelude for your homeworks or your second quiz in that section. So thank you very much, and we'll talk to you again for beams and possibly a treatment of a tapered shaft. So see you then.